All right, so let's start. So last lecture, we were looking at current gain, and we had seen that there are several components to the current gain, and the most important one, at least at moderate current densities, is the one which arises due to injection of holes in an NPN transistor into the emitter here. So that's the component which is dominant. And when we look at the expression for the current gain, we note that there are several factors, and there are diffusion constants, there are dopings, there are thicknesses, and this comes about because of band gap narrowing. So if you, and with the example that we were discussing, we had obtained a current gain which was fairly low, value of around 34, 35 or so for the doping and thicknesses of interest. And therefore, there is an interest in increasing, obviously, the current gain. 34 or 35 is too low a value, and we would like to increase it. One of the ways in which we could increase the current gain, note that the doping in the emitter is already very high. So one of the ways in which you could increase is, for example, you could decrease the doping in the base here, decrease the doping in the base, or decrease the base thickness here. And we were discussing in the last lecture that if you do that, if you decrease the base thickness or you decrease the base doping, there are consequences. And one of the consequences is what we are going to discuss today, which is the base width modulation or the early effect. And the idea here is this is the typical collector versus collector emitter voltage, right? And you know, these are of course being shown for different values of base current. And what we note here is that the collector current is not a constant with collector voltage here. There is, you can clearly see a slope here. The slope is there, and so the collector current is increasing with collector voltage, right? And so this model that we had derived, that IC equal to you know, the saturation current exponent VB by VT minus 1, is obviously not complete because we are seeing a dependence on collector voltage here. So we have to add another term which denotes the collector voltage term part here. All right, so we have to add that. And you know, this is the same graph here, but then shown you know, on a different scale, where, you know, now note earlier the scales were we were going from 0 to 10. Now if I show the same plot on a scale which is 0 to 20 here, and then on the other side is going up to minus 60. So now you can see the slopes very prominently. And if we take each one of these graphs and we extrapolate it here, all of them merge at one single point, which we know is the early voltage. Okay, and therefore what you are seeing is that the slope of this particular line, so this is practically a linear variation, and linear variation, and the slope then at any particular point, for example, if I'm looking at what is the slope here, the slope will be equal to IC, collector current at that point, divided by VCE, whatever collector voltage is there, plus a value which is the early voltage here. And one could describe this by a very simple model as IC equal to whatever was there earlier, and we add a term 1 plus VCE by VA, and VA is the early voltage that you see. Okay, so what it says is for different values of base emitter voltage, different base currents imply different base emitter voltages here. All of them, if you go to VC equal to minus VA, the current will extrapolate to 0. Right, so that's what this particular model says. If you put VC equal to minus VA, the current becomes equal to 0, extrapolated value becomes equal to 0. So this is the model that we have to describe this phenomena that in active mode, as you increase the collector voltage, the current increases, which is described by this early voltage here. So what we would like to know is, and you know that you would like the slope to be as small as possible because the slope signifies output resistance. And we know that in amplifiers and other places you require very low slope here. implying very high output resistance. So you're looking for VA to be generally high, as high as possible, right? And the higher the VA is, the higher the output resistance, and the higher the kind of gain that you can expect from an amplifier stage here. So VA is an important parameter, and we would like the value of this early voltage to be high. All right, so we would like to know what does VA depend on. Okay, so what we'll do is we'll do a simple derivation for early voltage. So this is the diagram that we frequently use for an NPN transistor. The depletion regions are shown on the two sides, base emitter, base collector. And what we are also showing in active mode, the electron density which is injected into the base is profile. The electron density is high close to the base emitter junction because it's forward biased, and the electron density is very low. We'll take it as 0 at the collector base junction. So that's, and because there's very little recombination, we have a thin base, so the electron density profile is linear. All right, so it's linear, and therefore the collector current, which is nothing but the electron current which has been injected, the same current flows into the collector. So the collector current then is, we know that this electron current is a diffusion current, and therefore the collector current is equal to diffusion current. So Q times dN times the gradient of here, delta n by delta x here. So delta n 0, we'll take this point as 0, divided by WB and multiplied by the area. So that's the collector current. And we know that collector current is changing with collector emitter voltage. So what we are going to do is keep this voltage constant here. The voltage across base emitter junction will keep constant, and will increase the collector voltage here. So what happens is, note, as I increase the collector voltage, I'm increasing the collector voltage, which means I'm making the collector base junction more reverse biased. More reverse bias means depletion width will increase. So let's say the depletion width becomes like this here, right? Depletion width has increased. So my base width that you see here, the effective base width, now extends only till here. Base width extends only till here. And at this edge now, my carrier density will be practically equal to 0. And therefore, the slope that you see here, the slope becomes like this here. The slope of this. So here the carrier density is constant. Why? Because we are not changing this voltage. Base voltage is not being changed. So carrier density at this point remains fixed. We are changing the collector voltage, so depletion width extends. And wherever is the edge of the depletion width, we are saying the carrier density here is negligible. So now with that in mind, the slope here changes. And as the slope changes, as you can see here, so the collector current remains QADN, delta N0 remains the same. What has happened is effective base width has become smaller. Effective base width has become smaller, and therefore we get a larger current. Right? So that's the phenomena that we are talking about. And we call it the base width modulation. So base width is being modulated by what? By the collector voltage. So as you change the collector voltage modulates the depletion region, which then modulates the effective base width. And note that the whole phenomena revolves around the this depletion region changing with respect to the collector voltage here. And note that change in depletion charge with the applied voltage is what? Depletion capacitance. So you know that this whole phenomena will be related to the collector base depletion capacitance. So when we arrive at an expression for early voltage, you would see that it's related to the junction capacitance. All right, so what we like to do is now do the derivation here. Okay. All right, so this is the expression for current. AQ, and we said AQ dN by WB multiplied by what? Delta N0. Go back and see delta N0. Delta N0 is what? Ni square over Na exponent VB by VT. So that's the expression for current. So current now, if you note, what are we doing to the equation? I'm trying to bring the current into a form where I can relate it to depletion charge, change in depletion charge versus voltage here. So note that what I've done is multiply by Q, and then we have QNA, and I've taken WB here. So we get a term which is QNAWB, right? And this is the term, note, that will change with the collector voltage. Next, I'm writing this as IC equal to K by QB. QB is what? Q times NA times WB. Right? So all other terms I'm not interested right now because they are constants, VBE and Q and NI and DN and all are constants. So we all lump it into a parameter K divided by QB, and QB is QNAWB. All right? So a change in collector current versus collector emitter voltage is same as change in collector current with collector base voltage, because collector emitter voltage is what? Sum of collector base plus base emitter. And base emitter we are keeping constant. All right. So that we keep constant. So delta IC by delta VCB. Take its derivative. So you get minus K QB square delta QB by delta VCB. So delta IC by VCE is equal to K by QB is nothing but IC. So we write IC here. 1 over QB minus del Q by del VCB. Right? So that's the del IC by del VC. Now we know from this expression that del IC by del VCE should be equal to, according to this model, equal to IC by VA. And therefore, we can relate these two together and get VA, 1 over VA is 1 over QB minus del QB by del VCB. So if we can find this QB, we already know. QB is QNAWB. We already know what it is. Now we have to take its derivative with respect to VCB, and therefore we'll get an expression for early voltage. That's all we have to do. Okay. All right. So let's do that. VA is 1 over inverse of VA is 1 over QB minus del QB by del VC. Okay. All right. So let's look at this term here then. What is QB? QB is, now I can write the following. The total base charge, total charge in the base here, so will be equal to QB0. QB0 is what? Total charge from this edge to this edge here, which is equal to QNAWB0 minus the charge, depletion charge here, which we call as QJE, minus the depletion charge here, which is QJC. So note that QB is nothing but the total charge in the neutral region, total Q times NA times WB. That's, we are talking about this point here. So this charge is equal to total from here to here, this one, minus the depletion charge here and minus the depletion charge. Right? So we can write QB in terms of this. QB0 is a constant. The moment I write QNA, NA is a constant, WB0 is a metallurgical base weight, is a constant. QJE, note depletion charge here is a constant. We are not changing the base voltage. Emitter is constant. So this is a constant. So as you change the collector base voltage, what changes is this QJC, this depletion charge here. That is what changes. Right? So it's easy now to see that derivative of QB with respect to VCB, it will be nothing but, because the other two terms are constant, will be equal to derivative of QJC versus VCB, and which is nothing but junction capacitance. That's the definition of depletion capacitance. Change in depletion charge versus the change in voltage applied across that particular junction. So I have VC here and I have base voltage here. So that's the, by definition, is the junction capacitance here. Okay. So early voltage then will, according to us, then VA inverse, note that VA will be equal to QB divided by this term here, and this term we have already calculated is equal to CJC, and therefore early voltage comes out to be equal to QB times divided by CJC. That's the early voltage here. Makes sense that there is a, it's like a capacitive relationship. Voltage is equal to charge divided by capacitance here, and that's how you can remember it very easily. Voltage equal to charge, charge divided by capacitance. What is the capacitance? The collector junction. So you write CJC. What is the charge QB? Well, the charge here in the neutral part here, which is equal to QNAWB. The next thing is, well, we have already seen for a PN junction that this is the capacitance that you get. For any junction here, the capacitance goes as QES by 2 VBI plus VCB, NDC, NA. These are the dopings on the two sides here. And that's the expression for junction capacitance. And QB is QNAWB. So there we have a model for early voltage then. All the parameters are known. Doping in the base thickness, VBI, VCB, these are all known quantities. Dopings are known, of course. So all you have to do is evaluate this CJC, plug it here, multiply by QNAWB, and you get the early voltage here. Okay. So that's a simple model for early voltage here. Now the model is general. QB by CJC is general. If I had non-uniform doping in the base, instead of writing QNAWB, what I can do is I can do an integral Q times an integral of NAX versus from this point to this point. I could have integrated also and the expression would have been the same. All right. So, yeah. What? The base collector voltage, yes. What is constant? Early voltage remains, yeah. Right, it does depend, but it's a weak dependence. Yeah, that is true. Yeah, this is, note that not only this CJC, but as you keep on changing the collector base voltage, even WB also here changes. So WB also changes here, this also changes here. So there is a dependence on early voltage is not a, this thing here. But note the change that we are talking about is small. We are not talking about big changes here, okay? All right, so we were discussing a transistor where the doping in the base was 5 times 17, the doping in the collector was 10 to the power 16. And if we take these quantities, and we were talking also about a base width where for the typical condition that we were looking at, 0.8 volt forward bias here, the base width was 0.163 micron. And if we take all, and with these values, we can evaluate the junction capacitance. It comes out to be 20 nanofarad per centimeter square. And finally, if we put all of them together, early voltage for us turns out to be 66 volts here. Okay. So that's the value that we end up getting, 66 volts of early voltage. Okay. All right. So, you know, a fairly simple derivation and an easy to remember equation, except for CJC, slightly longer term. Okay. So as I said, now these are the dopings that I just showed you. This is the base width 0.163 that we get. This is the junction capacitance. And this is the early voltage here that we get here. Now, what I want you to do is the following. Again, as usual, take out a sheet. Suggest ways of doubling the early voltage. How would you double the early voltage now? 66 is, let's say, is on the lower side. I want, instead of 66, I want 130 volt. All right, 130 volt. Early voltage of 130 volt. I want to double it. And what will be the side effect, right? Or what will be the trade-off? We want to do this quickly. All right, so this is the expression for early voltage. And I want to double it. So I don't want you to calculate the actual values. Very simple. What are the factors? What are the different strategies for doubling early voltage? Note the doping levels though. 5 times 17, 10 to the power 16. If you look at the doping levels and you want to double the early voltage, what strategy will you use? General strategies. Okay, so obvious, looking at this expression, you would try and double NA, right? Huh? If you double NA, you think early voltage will double? there are going to be some effects on WB. The moment you double Na, WB will change. The value here will change. Why? WB is equal to what? 0.2 micron minus the depletion width on the emitter side minus the depletion width on the collector side. The depletion width will change. Depletion width on the two sides will change. These values will change here. And therefore, this value will also change. Right? So you have to take that into account. So, as a, let's say as a complete assignment, if we are not doing it qualitatively, you'll have to then take into account by how much should I double Na. If Na is your strategy, by how much should I increase Na, taking into account the fact that WB will change. Okay, WB will change here. All right, so you have to do that. If you look at CJC, if you look at NDC, Na, and Na plus NDC. Now, look at the ratio here. This is 50 times higher than the collector doping. So, Na is not going to have an effect here. Na will drop out. So, collector junction capacitance will not change. And as you try to double Na, WB will, what will happen to WB? Will it increase or decrease? Decrease. Look at it as you look at this. WB is what? WB is from here to here. Is equal to the total metallurgical width minus this one here and minus this one here. As you increase the doping, depletion will become smaller and WB will actually increase, right? So in a way, it helps you if you simply double the base width, right? You know that WB is also going to increase, so you'll get more than double the early voltage, right? You'll get more than double the early voltage. So that is fine. I mean, you're aiming for double and you simply double Na, you know that you're going to get more than that. All right, so that's fine. All right, so, but then that's easy, right? I've increased the early voltage. What is the side effect? Current gain. Because you've doubled Na and WB also you've increased, so the current gain is going to drop further. The current gain, remember now, current gain is going to drop because current gain is inversely proportional to Na, inversely proportional to WB. Both these factors, current gain is inversely proportional to both of them. So current gain is going to drop, right? So that's the side effect that you will suffer from. All right, suppose I don't want to touch Na. What is the other factor? Let's stick with the base. I'll double WB, double the base width. Again, current gain will drop. That's one drawback side effect that you'll see. WB current gain will drop. What else will happen is what we'll see shortly, that as you increase the base width, the transistor gets slower. The frequency response of the transistor suffers as you increase the base width. We'll see shortly today. So that's the other consequence that you will get. So that's why the moment I either double Na or double WB, the current gain goes down and my transistor gets slow, especially when I do WB, right? So then, then you're saying, well, perhaps I shouldn't touch this. The base, I should not touch this. Maybe I should focus on CJC. What do I need to do here? CJC, what will you do? You want to double early voltage. Make the only thing you have is ND, doping in the collector. What do you do doping to the collector? So Na plus NDC is practically Na. Na cancels here, so it's square root NDC. So what do you do to the doping? Cut it down by factor of 4. Right? Factor of 4, if you cut it down, what will happen then? Fine, you'll get an early voltage which doubles. Collector doping. Right? You go back, collector doping, if I cut it down by a factor of 4. Anything that you can think of? Depletion width will become larger. Fine. But how does that matter? Well, again, that's the I mean, current gain doesn't depend on this, so that is not an issue. But what we'll see again today, that if you look at an electron, as it has to travel, in the emitter region here, this is of course neutral, so there's no issue. It has to travel through the depletion region here, travel through the base, and then travel through the collector depletion region. There is a delay associated with an electron going from one edge of the depletion region to the other end and then getting collected here. There is a delay which we will see, which involves what we call as collector transit time. Amount of time it takes for an electron to go from this edge to this particular edge. And now what is happening is, if you decrease NDC by a factor of 4, the depletion regions become larger by a factor of 2, and the collector transit time becomes larger by a factor of 2. And therefore, your transistor gets slower. Transistor gets slower again. So, which is pointing to that we have seen now current gain. We have seen the early voltage, and what we need to see is now the frequency response, because that's another very important part here. Yeah.
What if I make a part of the collector? What if I make a larger collector as part of the collector unload? It's like inserting a
Sure, I region. Right.
I region in the depletion.
Okay.
That brings from the.
So you'll bring down the collector junction capacitance, right? So as you bring down the junction capacitance, you've inserted a layer, right? So the electron has to go through that layer. So it's a transit time. That's what I'm trying to point out, that there is a transit time which comes in as the electron goes from one edge to the other edge here. A transit time which adds to the overall delay here. So that's what you suffer. That is the point that I'm trying to make here, that the trade-offs, early voltage is important for you. So either you are losing the current gain. You may lose if you just simply increase NA. On the other hand, if you simply increase WB, you lose current gain plus the base transit time. It has to go through the base, and the base becomes thicker, and the time it takes to travel across the base, that becomes large, transistor gets slower. Then the other one is you decrease NDC. Well, you don't affect current gain. Early voltage goes up, but then you increase collector transit time. Not only that, another thing that happens is there's always an upper limit at which the transistor, in terms of current density. If you keep on increasing the current in a transistor, a stage comes where we have high level injection and transistor doesn't behave well. Now we'll see, I think we are short on time, but so I'm just probably going to state the result, that what is the highest collector current that you can apply, it does depend on what is the doping. If you have collector doping which is small, you can't go to very high current densities. If you have collector doping which is high, you can go to high current densities. So you don't want to reduce the collector doping too much. And all of this will make more sense if we go and look at the frequency response. Okay, so here all that we can very clearly see that there is a current gain, early voltage trade-off. The two of them are related together. You get high early voltage, but then you get current gain. So that's why, if you're looking at how good is my transistor, one of the ways of looking at it is how large is the product of current gain and early voltage. Don't just look at beta. Somebody may give you a very high beta, but will give you very low VA. A good transistor would be where the beta times VA product itself is very high. That would be a good design, where beta dot VA is high. Okay? It's very easy to give a high beta, but then very low voltage, early voltage, or very high early voltage, low beta. If somebody gives you high gain and high early voltage also, I mean, that's a good transistor. That's a good design, and that's something that, and if the person is asking for more money, well, you may agree to pay for that, because it's a high beta and high early voltage, both of them at the same time. Okay, so that's a challenge, how to get that. But you know that it's not the complete story, because somebody may give you higher beta and higher VA and make the collector doping very small, right? Make the collector doping very small, and therefore will give you very high current gain, high VA, but a very slow transistor. A very slow transistor. because collector transit time is very high. So he'll give you a very slow transistor. So you know that this is not the complete story. If you want to, we have something called figure of merit. If you want to evaluate different transistors, right? Somebody will give you some beta, some early voltage, some frequency response. How do you compare one transistor to the other? All right. So we have something called figure of merit. It does depend on application. So you know that in addition to beta and VA, maybe I should, I don't know, multiply it by the frequency response. If somebody gives you high beta, high VA, and high frequency, anybody remembers how do we characterize speed of a bipolar transistor? What parameter do we use? Not for an amplifier, but for a transistor itself. Huh? Unity gain frequency, FT. So somebody gives you high beta, high early voltage, high unity gain frequency. Well, now that's a really good transistor. But if high beta, high VA, and a low VT, low FT, well, then not as good, right? So you have to look at all three parameters to compare the one transistor with the other. All right. So the moment, so we have seen beta, VA, we have to come to frequency response. And frequency response means you have to look at capacitance. Right? So frequency response in all places is nothing but an RC product. Keep that in mind. In almost all semiconductor devices, it's an R and a C. Some R and some C. Okay? So bipolar transistor is nothing but has two diodes. And so you have to know that in a diode, there can be two capacitances here. One is a junction capacitance or depletion capacitance. The other one, if it is forward bias, we have diffusion capacitance. So what I'm going to do is quickly, this is something that we've already seen, just to refresh your memory. So junction capacitance is what? We have a depletion charge here, and the depletion charge, change in depletion charge with change in voltage gives you a junction capacitance. Okay? And we have this expression for junction capacitance, which we spent some time deriving it. And we said a more general expression for capacitance is Cj equal to Cj0, 1 minus Vj by Vbi raised to the power m. M depends on the doping profile. So that's the junction capacitance. We will always have, whenever we have a PN junction, we'll have a depletion capacitance. All right. So that is always there. The other one was, if you take a forward bias junction, then you are injecting holes here. It shows excess holes here. And you are injecting electrons here. You have excess electrons here. And therefore, you have an excess hole charge, which is QP. And you have an excess electron charge, which is QN. Right. These regions are neutral. So as we said, this region is neutral. So there is an excess hole charge. So it is balanced by excess electron charge also on this side. So there is QP and there is electrons also on this side. So the region is neutral. And when you change a voltage, you have to change the charge here because the charge is related to voltage. The holes will come from here. So you increase the charge. The holes will come from here. And this region is neutral. The electrons come from here. And therefore it manifests itself as a capacitance again. And what we can do is we can look at these charges here and we can find out how these charges change with voltage. And we have a diffusion capacitance which says these charges, excess charges that are there, how do they change with voltage here? That gives rise to diffusion capacitance. And so diffusion capacitance under quasi-static. So this is something that we have done earlier. What we can show is diffusion capacitance is equal to Q by KT current times some lifetime. Basically, it is diffusion capacitance is the charge, excess charge, how it changes with voltage. And one can express it finally in terms of this kind of an expression. All right, so let's come back to our, all this we have seen here. Let's come back to a bipolar. So when I take a bipolar, I'm talking about bipolar in forward active mode. Collector base junction is reverse bias. Base emitter junction is forward bias. Now we can all see now the capacitances. This is reverse bias. The only capacitance that I will have is CJC, junction capacitance. Okay, so that's between base and collector terminals here. I have a diode here, and therefore I have a depletion capacitance CJE. But then this diode is forward biased. Forward bias, and the moment you forward bias a diode, you will have a diffusion capacitance. So we have a diffusion capacitance also, right? So these are the capacitances that are there in our transistor. This is very easy. CJC is nothing but the same capacitance. And so this is capacitance per unit area. We have multiplied by the area of the collector junction here. And same thing with base emitter, this capacitance per unit area multiplied by the emitter area. So the reason why I've put emitter area and collector area, because if you remember, the emitter is smaller, collector is larger, right? So the areas are not the same for collector and emitter. So these are very straightforward to write down CJE and CJC. This is more interesting, diffusion capacitance here. All right, so this is what it shows. CJE is here, CJC is here. Note that area for collector junction is larger as compared to area of the base emitter junction here. So that's why the areas have been explicitly written AC here and AE here. Okay, all right. All right, so diffusion. So let's focus on this one here, diffusion capacitance here. So when I forward bias my junction here, note that electrons were injected here. So there is an electron charge here, and holes were injected here. There is a hole charge here. These are the diffusion charges. Now we know that emitter, so diffusion charge is where Q diffusion is nothing but QP here and QN here. But we know that emitter doping is much higher than the base doping. You know, factor of 50 or factor of 100 higher. So therefore, the minority charge here is much smaller than the minority charge here. And it's a good approximation to say the diffusion charge that I have is, I'll take only QN into account. This one is going to be small. Okay, one can take QP also into account, but as a first order approximation, we'll keep QN. Now, do we know how to calculate QN? What is that charge? And diffusion capacitance will be equal to what? Change in this charge with change in base emitter voltage. Note again, I'm emphasizing this region is neutral. There are electrons here, and the electrons are compensated by the holes here. If you increase base emitter voltage, more electrons will come in, and more holes have to come in from the base here. And that's why it manifests itself as a capacitance. Okay. So Qn is nothing but, if I have to take Q, and it's because of the excess electrons, so I have to integrate the excess electrons from this edge, from 0 to this edge here. All I have to do is integrate it. So let's do that here. Let's look at this picture. We've been saying that electron density at this edge is high. We know the value. Ni square over Na exponent QVB by KT minus 1. The electron density at this edge is negligible. We are taking it as 0. So that's how electron density is going. Qn is nothing but the integral here of excess electron density. So that's equal to Q is area under the triangle, half delta N0 multiplied by the base width. And if you want charge, total charge, you multiply by area. If you want charge per unit area, then of course A is not there. So that's Qn. So straightforward to calculate Qn. IC, we know collector current is nothing but the slope here, Q dN by WB delta N0 times the emitter area. It's a diffusion current. So that's the collector current here. And you can clearly see that collector current and the charge are related together. This depends on delta N0. This also depends on delta N0. The rest are all constants. I can take the ratio and you see that Qn equal to IC into tau B. So the charge here in this region is related to collector current, linearly related to collector current using a constant tau B, which is WB square over 2dN. You can verify that this has the units of time. And this is what we call as the base transit time. This much charge is stored here and it results in this much current here. Right? So the ratio of the two is equal to the transit time, which is WB square over 2B. All right. So we've obtained an expression for now Qn equal to IC into tau B. Tau B is WB square over 2dN. Now all we have to do is take the derivative. Derivative of Qn versus VBE to get the diffusion capacitance. And derivative with respect to VB. So what I can do is take derivative with respect to collector current and take derivative of collector current with respect to VBE. This we know is transconductance, change in collector current with change in base emitter voltage is transconductance. And del Qn by del IC is nothing but tau B. And therefore, we obtain CDE, diffusion capacitance is equal to tau B, QIC by KT is equal to GM tau B. Diffusion capacitance is equal to transconductance multiplied by base transit time. Okay. So straightforward, once you know the electron density profile here, you have to integrate the electron density profile, and it's easy to show that diffusion charge is linearly related to collector current, and then it's a simple derivative which gives us what is the CDE equal to, diffusion capacitance. Okay. All right. So what we are showing is this Qn that you see here is diffusion charge located here in the base. But note that, as we said, the holes, the electrons are injected here, and they have to move through the depletion region and eventually get collected here. So there are going to be electrons in the collector also. If I don't have electrons in the collector, then how is the current flowing? All right. So the idea is I have a charge here also. Just like I said, there is a charge in the base because those are the electrons that give rise to collector current. I must have a charge here also. Otherwise, how will the current flow? So just imagine the following here. Just imagine that I had not applied any base emitter voltage, right? Don't apply any base emitter voltage here. So let's do that following. All right. So don't apply any base emitter voltage. There's no current flowing. There is no charge here, right? Apply a base emitter voltage. Electrons get injected here. They're diffusing in this region here. And then they come to the collector. What do they see? They see a large field. And the field, what does it do? It sweeps the electron through the collector depletion region, and then they enter N region. The moment the electrons come here, the moment one electron will enter into this particular region, what will happen? In the N region. It starts from here and enters into the N region. What does it do? Is there a delay involved in an electron going from here to here? It enters an N region. What does it do? I mean, if you think about, suppose I just ask you a hypothetical question. I have an N, right? Two contacts here, right? I somehow, it's an N region here, I inject an electron. Suppose, what will happen? If I inject here, this region is neutral. I inject an electron, what does it do? It creates a charge imbalance, right? And what does it do? This electron will do? Immediately, it will push out an electron from this. There's no delay. In fact, it's like a charge wave which travels here at almost at the speed of the electromagnetic wave in that particular medium. Okay? So the moment an electron enters here, one electron will come out, there's no problem. So that's not a delay. Right? So what happens is there is a delay for an electron to go from here to here. And we'll soon see that there is a delay involved in electron going from this edge to this edge here. Okay. So what I'm saying is there is a charge in the collector. There is a charge stored in the collector. How do I calculate that charge? Remember, what we are saying is in the depletion region, the electrons will flow. And because the field is high, the current will be predominantly drift. Right? So I have whatever collector current is flowing will be equal to Q times the charge density here in the depletion region. QNC, mobility times field. Right? I have a current flowing, and therefore I must have electron density inside the depletion region. Now, if the field is very high, what happens to mu times F? If the field is high, people remember drift velocity. How does it go with field? It saturates. If the field is high, then you don't say mu into F. There is a velocity here, saturation velocity. So what you do is you write it as QNC times V sat, which is equal to mu times F here, is saturation velocity. So how many electrons are there in the collector depletion region? NC equal to JC by QV sat. These many electrons are there in the depletion region. They have to be there, otherwise no current can flow. Now, if V sat were infinite or very high, then the amount of NC will be very small and I can forget about it. But if VSAT is not very high, then I have significant amount of NC here and there is a charge in this particular region. Okay. And remember one thing, what is a capacitance? Is change in charge with voltage, right? Anytime you have a charge and if you change voltage and the charge changes, you have a capacitance, right? So now, where have these electrons come from? Where have they come from? They've come from the emitter. As you apply the voltage here, they've come from here. So if you look at Q and C, if I change base emitter voltage, will this charge change? Change base emitter voltage, right? If you change base emitter voltage, what changes? The collector current changes. Collector current changes what? Exponentially with base emitter voltage. So if you change your base emitter voltage, collector current increases exponentially. NC also increases exponentially. So we have a charge now. What we are talking about, how much charge do we have in this region here? We are talking about a charge equal to Q times NC, this is an approximate expression, times the depletion width here, XDC here. We are assuming that almost the entire depletion region width is in this particular side here, N side here, because N doping is very small. So we have a charge stored here. Q and C is this, Q times NC times XDC. And NC we know is JC by VSAT. JC by Q VSAT here. So we have Q equal to XDC VSAT into J. Right? And you can see clearly that this has the units of time. Distance divided by velocity has units of time. So what we can do is, we can write this as, this charge that you see here is equal to some tau C because it's associated with collector times JC. So we have a charge stored even here, and the charge is equal to what we call as the collector transit time. Collector transit time multiplied by a current density. All right. More accurate analysis, which will take some time for us to show that tau C is not equal to the total depletion region divided by VSAT, but is actually depletion width divided by 2 VSAT. Okay, I'll post some notes, supplementary notes, which will show you why it is not this, but why this additional factor of half comes in. Okay, so that will require some little bit of more analysis to show. But the point is that I have a charge here which changes with collector current, and therefore I have a capacitance. Capacitance is nothing but change in charge with voltage here. So I have another capacitance which is equal to Gm times tau C. So my total, what is showing? Okay, so I'll skip this and show you later on. So this is what is happening now. This is a complete picture of bipolar transistor now. The junction capacitance CJE, CJC here, and diffusion capacitance now has two terms. One, Gm tau B due to charge here, and Gm times tau C, which is charge in this region. Okay, so we have this, and this tau B is WB square over 2dn, and collector transit time is XDC by 2 VSAT. So now we have all the capacitances except for one more capacitance, which is the substrate capacitance here, which you can see from this picture here, which is not apparent from a 1D picture. But if you look at this particular picture here, I have emitter, base, and collector, and we forget about the fact that there is a substrate also in a bipolar transistor. There's a substrate here, and it shows two bipolar transistors. The substrate is there, p-type, to isolate one transistor from the other. And between the collector and substrate, there's another capacitance, which is again, this is kept reverse bias. So this is a depletion capacitance. All right. So that's the final model that we have. 1, 2 here, 3, and 4 capacitances. And this one, diffusion capacitance, has two terms here, Gm tau B plus tau C. So now in the next lecture, what we'll do is, we'll take this particular model, and we have seen something like this. We'll take this particular model. We can get a small signal model. Let me just tell you what you'll get. And once you get from a small signal model, you can calculate unity gain frequency. And unity gain frequency will tell us finally that unity gain frequency has all these terms here. Tau B that you see here and tau C that you see here. So all these terms contribute to the unity gain frequency and the delay here. All right. So okay, let's stop.